Yep, good. Yeah, we're good. It's on the screen. All right, so our next speaker is Jason Osborne. Jason is a professor of statistics at North Carolina State University, where he was hired as a consulting faculty member to spend a third of his time designing experiments and analyzing data for faculty and students in the life sciences. He enjoys cycling while his knees still allow him to. He roots for the Astros, the Rockets, the Steelers, and the students from the department who've gone to work in the sports analytic industry. So he's going to talk about baseball. So take it away.
Thank you. Thank you for that introduction. Is the microphone okay? Okay. Okay, this is joint work with Rich Levine at San Diego State. As the introducer said, I'll be speaking about baseball, in particular home run park effects adjusted for personnel. And I'll say that in Mark Lichtman's dichotomy of 2007 versus 2025 editions of NESSIS, this might be more like the 2007. It's straightforward Poisson regression modeling. Okay, so our home run park factors are of interest to fans, front offices, and the podcasters to whom I listen won't stop talking about them. Every ballpark is different. Some are friendlier to home runs than others. Here on the left, we have a West Coast park you may recognize as Oracle Park in San Francisco, home of the Giants. And on the right, we have Fenway Park here in Boston, where the team clinched a berth in the playoffs last night. And I was surprised in speaking with some of you before the talk that folks who aren't baseball fans maybe didn't know how different baseball parks can be. You can see these are both asymmetric, and the asymmetries are different. And I sat behind pesky pole last night on the right field line in Fenway and was astonished at how close it was. You can find these diagrams to your heart's content at andrewclem.com. Wonderful website, hundreds of years worth of diagrams. So this work is to some degree motivated by this quote from, of course, the fantastic book Analyzing Baseball Data with R in the 3rd edition. I'm just going to read the quote directly. The parentheses are those of the authors and not mine. Finally, the proposed park factors, as well as most published versions of park factors, essentially ignore the players involved in each event. In this case, the batter and the pitcher. So that's what we set out to do, is to take account of who's hitting and who's pitching. So thanks to Retrosheet, Chadwick, and the aforementioned authors for helping make these data available. We have 15 seasons worth of data, 34,000 games. We excluded international games played in stadiums we're not studying, and we took Joe Robbie Stadium out. 2.66 million plate appearances, 76,000 home runs for a rate of about a home run about 3% of the time, or 35 plate appearances per home run, which, if you break that .029 down by the handedness of the batter and the pitcher, which I will call matchup from here on out. Matchup is the combination of handedness of batter and pitcher. You can see that it varies by handedness. Baseball fans, of course, know this. Lefty batters seem to hit home runs less frequently against lefty pitchers. And then if you arrange it in a 2x2 table, you could glance at the marginal means and see not much of a difference marginally for lefty pitchers versus righty pitchers. But of course, that difference depends on the hitter and vice versa. And then if you look at the plate appearances in a 2x2 layout as proportions, once again you see not only are home runs rare for lefty-lefty matchups, but the matchups themselves are relatively rare, occurring in only 8% of plate appearances. So we say the effects of the batter-handedness and the pitcher-handedness are non-additive, both on the rate of home runs and the frequency of plate appearances. So here I just juxtapose that breakdown of plate appearances by matchup with those for Progressive Field in Cleveland, and this astonishes me that more than half the plate appearances in Progressive Field over a 15-year period were hit from the left side of the plate. So if we're going to compare ballparks, it's not enough to just compare them for lefty and righty batters. You really need the combination of batter and pitcher. So in the model we put forward, we will adopt as the observational unit, not the game, but the combination of game and matchup. So usually we'll get 4 observations per game. So we'll let Y denote the total home runs hit in a game matchup. We'll adopt a generalized linear mixed model with Poisson response. They're not really independent, but conditionally on a random season effect, we'll assume observations to be independent. The log of the mean number of home runs hit will involve random season effects, personnel effects, which I'll have to talk more about, and the handedness by park effects. So there are 30 parks and 4 handednesses, so this will involve 120 parameters. So quickly, we define indicator variables for season, X1 superscript S, and handedness of the batter and pitcher, and park. And then again, I'll say more about these covariates for how good the batters were and how good the pitchers were and how many of them there were later. But for now, the model says that the mean on the log scale is equal to an intercept plus this sum of season effects. So the S's are random variables, X's are indicator variables, plus these personnel effects, the covariates. And then this looks complicated, but this is all the season by handedness, park by handedness combinations. So for a given I, if you consider one observation, only one of these products of X variables is non-zero, so it's not that complicated. I did this with SAS. I work in a building called SAS Hall, so I'm obligated to use SAS. I used Proc-Glimix, generalized linear mixed models. I won't say much about it. There's the code. Sometimes it's easier to speak in syntax than it is in models, so this may be more comprehensible than the previous slide. I'll just note that park star, BH star, PH, park by batter hand by pitcher hand, means something different, I believe, in SAS than in R. This will not partition effects into main effects and interactions. It'll just be a single factor with 120 levels. In R, the code might look like this. You use the LME4 package and use the glimmer function to fit the model after having created this variable that's the combination of ballpark and batter hand and pitcher hand using mutate. I should say, if I could just as an aside, going from the first edition to analyzing baseball data with R to the second edition really brought me around to the tidyverse. Before that, I was resistant, but that book sure swung. So anyways, continuing on, the season effects, we just modeled with this random season term in the model. There may be trends locally. We didn't attempt to model them. I just point out that from 2014 to 19, home runs, for whatever reason, increased by more than 50%. So we need to worry about seasons, certainly in some way. How can we measure the home run ability of individual batters? Personnel effects. So certainly a reasonable thing to do is just divide the number of home runs hit by the plate appearances. But if the model has both home runs hit on the left side and this measure of hitting ability on the right side, that seems problematic. So what we'll do is something else. We will construct these elsewhere measurements where we compute an X variable for a batter based on all of their plate appearances not in the current park where home runs Y is measured. And I'll just show you the details of that. Consider the home opener at 2021 at Coors Field, bottom of the first inning. Current Red Sox Trevor Story's right-handed batter. In the 15 years of data we looked at, I don't care about how he did at Coors Field, but I do care about how he did away from Coors Field. That's what I'll use to measure his ability to hit a home run. So he has home runs he has 25 home runs when facing left-handed pitchers away from Coors Field. So that will be the X variable we use for that observation. Only there's one more step, which I'll mention momentarily. I'll just show you. This is what the play-by-play data might look like from RetroSheet. So all these codes mean things to people who study this. Basically, Trevor Story batted third in the inning against Clayton Kershaw, a left-handed pitcher. On a 1-2 count, he got a hit. He got a single. Event code 20 means a single. And here's the thing. I put these asterisks in here. We're going to measure his ability using these elsewhere home run statistics. So he's going to get a .043, whereas Clayton Kershaw, a left-handed batter when facing right-handed pitchers, rarely gives up home runs. His home run measure away from Coors Field, this isn't home and road, this is away from Coors Field, he gives up home runs against right-handed batters in 2% of plate appearances. So that will be his XP variable. And the remaining step is to aggregate over these plate appearances to obtain a single measure for each matchup for each game. So this aggregate elsewhere measure of batting ability is the sum over all the plate appearances in that game for batters of a given matchup. And similarly for pitchers, if I show you the data, it might be a little easier to understand. So for the first game on April 1st, no foolin', no home runs were hit. If you look at matchups involving right-handed batters against left-handed pitchers, like Kershaw, there were 24 in that game. If we measure the ability of right-handed batters to hit home runs against left-handed pitchers away from Coors data in Coors Field, including probably the 3 or so plate appearances by Trevor Story, they add up to .504. And this also includes, of course, the Dodgers, if any of their right-handed batters were hitting against left-handed pitchers that day. And I'll just point out that that isn't very strong. .02 compared to the rates we were looking at before is on the low end. So if you want to estimate the chance of a home run in Coors Field, you need to adjust for that. The fact that even though it's a homer-friendly environment, maybe the Rockies don't have the greatest hitters. So Poissonness, I fit the model, and here I show you a table of frequencies for those game matchups where the estimated or fitted home runs was about 1.4 after rounding. And here are the counts. There were 876 games with no home runs, 1,200 with 1 home run, so on. These are the relative frequencies. And then I compare those to the fitted values from the Poisson mass function and get pretty good agreement between these two columns. And then visually, you can see pretty good agreement. So this is 0 strikes against the Poisson assumption. And also the mean and variance are about the same, which is what we expect for Poisson data. One more plot is provided by Hoagland and Tukey, this Poissonness plot that involves this phi function where if we multiply the relative frequency by k factorial and then take the log, we should see minus lambda plus k times log lambda. We should see an increase in this phi function as k increases with slope log lambda equals 0.3. And here is the plot in red and the theoretical plot in black. The theoretical just has, line has intercept minus 1.4 and slope log of 1.4. And then they recommend if you have a singleton, only 1 game with 7 home runs hit, you don't want it to weigh too much in the plot, so you use a special symbol, a 1 or a 2 if you see that. And this is for all the values of lambda rounded to the nearest 0.2. So as we sequence along using the language of R, or the tidyverse, lambda, we should see a change in the slope that goes from negative for lambda less than 1 to positive. And you see that as you go across these. And you see they're pretty linear, and so no screaming disagreement with the Poisson assumption. Here's the fitted model, or part of it. So here's the intercept. Here are the slopes for how good the batters were and how abundant they were for a given matchup, and similarly for the pitchers. And let me call your attention to the relative magnitude of these two things. The slope is 2.6, suggesting that who the batters were matters more than who the pitchers were, by a factor of about 2.5 or 3. And this is in agreement with the aforementioned authors of Analyzing Baseball Data with R, who fit an additive random effects model for individual plate appearances for the chance of a home run, and find the ratio of estimated square root variance components is, if you will, in the same ballpark, to 2.8. And then, sorry to throw lots of tables of numbers at you. These are the 15 least friendly park regression coefficients for all 4 matchups. You don't have to pay attention to them for now. These are the 30 for the the 15 most friendly park coefficients. And let me just call your attention to the 0 in the rightmost column. So this is the Nationals Park, home of the Washington Nationals for righty-righty matchups. This is reference cell coding, so there has to be some reference. So all of these numbers are relative to righty-righty matchups at Nationals Park. So it's by default 0. The intercept is the right park effect for that matchup. And then I'll also call your attention to, just as a sanity check, what's going on in Yankee Stadium, where there's this famous short porch, where it's believed that it's easier for left-handed batters to hit home runs. So I note that for lefty-righty matchups, this coefficient here for Yankee Stadium is bigger than any other except the Great American Ballpark, so it ranks 2. And then for lefty-lefty matchups, it ranks 4. So as a sanity check, that's reassuring. These park effects parameters they make sense. So how do we use them? How do we use this model to estimate the mean number of home runs in a single game in a given park for a given matchup if the personnel were average? And this so-called adjusted mean that we use in analysis of covariance. So this is not just adjusting to average personnel, but in average frequencies as well. So we just evaluate that complicated looking model with all the x variables at average values for the elsewhere covariates. And it turns out it's not that complicated. There's just a lot of symbols. So the adjusted mean for ballpark P and handedness matchup M on the log scale is this function of park effects, the intercept plus the park effects. I just showed you 120 park effects in 2 slides, plus the adjustment for personnel. So this is adjusting to average personnel and average frequencies. And then you exponentiate, and that is your adjusted mean. And then standard errors for all these things are directly available from the software. These are the average values of the covariates to which we will adjust the means. I note how small these values are for lefty-lefty matchups. Well, that is a reflection of the low frequency. It means the number of plate appearances that we're adding up is small. And this is the average of those sums in this table. And frequency, as I say, is built into these sums, these averages of sums. So just to make it concrete, here's Yankee Stadium, lefty-righty matchups. So over a 15-year period, an average of 1 home run per game was hit in these matchups with a variance of 1.25, 1,164 games. Relevant park effect, remember we were looking at this 0.16 in that table that ranked second only to Great American Ballpark. So, and then if I take the Z bar values from the previous slide, 0.76 and 0.77, and then plug it all into the model and exponentiate, I get this adjusted mean of about 0.86 home runs per game is the fitted value. Well, so this includes the park effect, so this includes our estimate of how easy it is to hit a home run for a left-handed batter in Yankee Stadium. So why isn't this 0.864 equal to this one observed empirical 1.017? Well, because the hitters at Yankee Stadium were quite different from average. That's the point. Here we're estimating the function at the averages of the Z's, but the players at Yankee Stadium were different. Standard error directly from output, and then this is what the output looks like if there are any SAS users. Then you might have seen this before if you've used proc Glimix or, yeah. So this is the mean we calculated and the standard error. So sorry about the sequel, but I'm going to bombard you with a table of numbers. I'll try to call your attention to certain elements from those tables. It's hard to manage two covariates at once, so I'm just going to take their sum with weights according to the slopes for batters and pitchers. Again, I'm sorry about this. I'm sorry it's so small. I'll try to direct your attention to certain elements. So first of all, that adjusted mean for Yankee Stadium for lefty-righty matchups, this whole table is lefty-righty matchups, appears down here in this 0.86. Sorry it's so small. And the standard error, the range of standard errors for these adjusted means is between 0.022 and 0.034. And I'll call your attention to three parks, Target Field in Minnesota, Progressive Field in Cleveland, and what's now called Rate Field in Chicago. I went to Northwestern, and we went to games at New Comiskey, it was called. And then I try to call your attention to certain columns as well. So for whatever reason, the plate appearances over 15 years at Target Field were such that the hitters who are left-handed when facing right-handed pitchers tended to yield a lot of home runs, ranked third in baseball. And their unadjusted empirical home runs per game was top 10. But if we adjust to a more average personnel on the field, they get their adjusted mean falls to the bottom 10 to 20. So it's a double-digit change in ranks. And it's even more pronounced for Progressive Field, where if you look at their ZB value in this leftmost column, it really stands out from all the other ZB values because they had so many plate appearances by left-handed batters. And they basically the personnel who played there were, when we measure them outside of Progressive Field, we would expect them to generate more home runs than the personnel at any other ballpark. And so as a consequence, they get adjusted from most home runs in all of baseball for lefty-righty matchups all the way down to middle of the road. So a double-digit change in ranks. And Rate Field gets adjusted from, I was looking for White Sox personnel in the audience. I didn't want to badmouth the White Sox. But the truth of the matter is that the batters and pitchers there have yielded more home runs for lefty-righty matchups, have yielded more home runs than any other park in baseball. Have fewer home runs than any other park in baseball. They're ranked 30th. So if more average teams were playing there and average frequencies, we would expect more home runs. And so their empirical home runs per game is ranked 18.5, but after adjustment, all the way into the top 10. For righty-lefty matchups, I call your attention again to a few selected ballparks. Anaheim, which the players who have played in Anaheim for righty batters, lefty pitchers, have, when measured outside of Anaheim, generated more home runs than any other park except one. They're ranked 2 except for Oakland. And so as a consequence, if we adjust them to a more average personnel, they'd be ranked down in terms of home run friendliness. And sure enough, they go from 11th unadjusted empirical home runs per game down to 21st, bottom 10. And so Mike Trout has hit a lot of home runs over this window of observation against left-handed pitchers. And so he's responsible to some degree for this too. In the same way that Aaron Judge is contributing to this this ranking for the Yankees. He's hit a lot of home runs of left-handed batters away from Yankee Stadium. Every plate appearance that he has in Yankee Stadium will be added up in our aggregation and contribute to this its ranking. So when we adjust for that, Yankee Stadium goes down from second highest empirical home runs per game, righty-lefty matchups, down by 9 to 11. And then quickly, Philadelphia, Milwaukee, and Cincinnati all get adjusted way up. Way up. Look at Cincinnati. In terms of just home runs per game, they rank 21st. And after adjustment, they rank 2nd. So that it's really just about the friendliest ballpark in the league for righty-lefty matchups, beaten only by Coors Field. Righty-righty matchups, just a few. So Toronto gets adjusted way down, and Dodgers, so I have to move on. So let me talk to you about marginal adjusted means. Sorry. So I argue that comparisons of parks has to be done matchup specific. You have to pay attention to the handedness of the batter and the pitcher. I'm sure people are going to, despite that admonishment, want to see a single number. And so you can get that with the marginal mean in a simple way because of the way the Z is constructed. You can just compute the adjusted mean for each of the 4 matchups and just take their simple sum, no weights needed. And for Yankee Stadium, it works out to an adjusted mean of 2.3 home runs per game. And and if you want to do inference for marginal means, you can't get it directly from software because this is a nonlinear function of 7 parameters, and you have to do the standard errors yourself using the multivariate delta method. It took me 50 lines of code. If you want to compare 2 marginal means, there's 11 parameters, and an editor asked us to do that, and that's these 3 most columns in the table of marginal means that you're looking at here. So this means that the Great American Ballpark was significantly more homer-friendly than 15 other less friendly ballparks after multiplicity adjustment with Bone-Ferroni. So even that conservative correction, we can still find a lot of significant differences if you want to do those pairwise comparisons. And then I'll just say Boston is harder to hit a home run in than you might think marginally. If you average over matchups in this way, it's bottom 10 in terms of home run friendliness. And then Dodger Stadium is noteworthy because it changes globs. It goes from not top 10 up to the top 10. What do I mean by glob? One of the podcasters I listen to uses this word to describe pitchers. There's pitcher glob and it's a good word, and he's actually pretty good statistically. So I'm clustering. I'm putting parks into groups according to this marginal mean in the same way that I assign grades at the end of the semester by looking at gaps here. And so that's how I drew these lines, and I call them globs instead of clusters because this is so informal. And you see 5 globs, if you will, of unfriendly ballparks on the left, sort of average ballparks here. Even though you should do this matchup specific, if you insist on averaging. And then these are home run friendly, and then Coors Field and the Great American Ballpark are in leagues of their own in terms of home run friendliness. So let me conclude quickly. I think the Poisson model provides a good fit. I think park effect estimates should be matchup specific. They're sometimes batter specific, but I think they should be matchup specific. It's not just batter hand, it's pitcher hand. We saw several double-digit changes after adjustment for personnel. You can implement pairwise comparisons or do other things using the multivariate delta method. It'd be nice to be able to use these park factors to adjust or forecast players maybe before a trade, and maybe this elsewhere approach to adjustment for personnel measures could be used for other measures. The paper is up on archive, and thank you very much to the NESSIS organizers. Thank you for your time.
We have time for one quick question.
Are you asking if front offices should try to optimize in different ballparks for different matchups?
Yeah, or is there any evidence that they are with, like,
I haven't looked at that. No, but that's a great idea. I am, so real quickly, managers don't want left-handed batters to face left-handed pitchers, even for good ones. And so they do tinker with lineups. I don't have an answer to your question, but I have an amusing anecdote. Managers just forever vary their lineups, partly in consideration with matchup. They probably should do it for Parks. But I just want to ask you, how many different lineups do you suppose the Pittsburgh Pirates used last year for the whole year? They got to face righty and lefty pitchers. How many lineups do you think they used, different lineups over the course of the year? Anyone? Two. Sorry, 154. Their favorite lineup they used twice.
Thank you.
Thank you.